All right, in this video I'm going to talk about sound. This goes right along with the sound notes. At the top of the notes you see a place where you have to write in just 9 characteristics of sound, and so that's what we're going to go through here. The first characteristic of sound that I think you know from the waves notes is that sound is an example of a compression wave or a longitudinal wave. In fact, sound is the most commonly given example of a compression wave, and the way that happens is this. Let's say that these are a person's vocal cords and they vibrate back and forth, right? And what happens when those vocal cords vibrate back and forth is there's air molecules in front of that, and it causes those air molecules to move as well. When those air molecules move, they hit the molecules in front of them, and those molecules move, etc., on down the line. You get a compression wave traveling in this direction. Remember, a compression wave happens because the direction of the wave is parallel to the movement of each individual particle. And so this particle bumps into this one, and that bumps into that one, that bumps into that one, etc., and it relays this compression wave that eventually falls on your eardrum, and you hear it as sound. These particles are vibrating back and forth against your eardrum senses it in the fluid of your ear as sound. So sound is a compression wave. Not only is sound a compression wave, but compression wave by necessity is an example of a mechanical wave. A mechanical wave, you need to write this down, is a wave that requires a medium to move through. It requires matter. Now light is not a mechanical wave. Light reaches us from the sun through the vacuum of space. There is no matter that light moves through. Light does not need matter to move through. However, if the two of us were standing on the moon and we could actually be on the moon without having helmets on, I could not talk to you on the moon. We could not produce sounds that could be heard because there is no air, there's no atmosphere, there's no matter through which sound can travel. Actually, I'm not 100% sure if the moon has no atmosphere. If you're in space, if you're in a place that has no atmosphere, no air, no matter whatsoever, sound cannot travel because there are no molecules to bump into each other. They cannot transmit that mechanical wave. The speed of sound is 330 meters per second in air at 0 degrees Celsius. And if you look in your formula chart, it tells you that the speed is 340 or 343, whichever the case may be, depending on how specific or accurate rather you want to be. 340 at 20 degrees Celsius, which means that as the temperature of the medium increases, the velocity increases. Now this brings us back to the point, remember, that the speed of a wave is only controlled by the medium itself. The only way you can change the speed of a wave is to mess with the medium. So remember, I had a rubber band rope and I sent a wave, a transverse wave for instance, along the rope. And I know this is a transverse wave and we're talking about a compression wave today, but it's the same concept. I asked you what I could do to change the speed of the wave, and many of you said simply increase the amplitude, which I did, but it did not change the speed. The only thing I could do is to make the rubber band tighter, and when I did that, that drastically increased the speed that the wave moved down the rubber band rope. Point being, the only way to change the speed of a wave, including sound wave, is to change the medium. So as the temperature of the medium increases, the velocity increases. We can also change the density of the medium. That increases the velocity as well. Increasing the density increases the velocity. Notice we're talking about the temperature of the medium and the density of the medium. I don't say temperature of air. The reason is sound does not only move through air, it moves through water, it moves through all solids, it moves through anything that has matter. If we increase the density of that wave, we can increase the velocity. And I want you to imagine something. Let's imagine that we all go outside in the hall and stand out there, and here we are, and we're going to try to transmit a quote-unquote sound wave from one end of the hall to the other. And the way we're going to do that is this person is going to touch this person, and this person will touch this person, and it goes on, etc., etc. The question is, does that touch transmit faster with less people or with more people? Well, the answer, hopefully you can figure out, is the touch. These people don't have arms. The touch transmits faster with more people because if you're this person, you actually have to travel a fair distance to get to this person. You may even have to run a little bit. Same thing here, we go to this person. In class, I said that this was the W hall. If we're out in the W hall and we want to transmit a touch from one end to the other, that's quite a long distance. If there's only 5 people to do that, it's going to take a while because I've got to run to the next person to touch them. Versus if we have like 55 or 100 people, it takes not quite as long, because if I'm this person, I get touched and I can touch the next person pretty quickly. I don't have to travel very far, if at all. And it's the same concept with a medium. With air, the molecules are very far apart, so they actually have to move a fair distance to contact the next molecule. Versus something like water or steel or something like that, where the molecules are very dense, they're closely packed together. The molecules have to move a very short distance to transmit that wave. Therefore, the wave will transmit much faster because the particles spend less time in transit between molecules. So the increasing density of the medium increases the speed of the sound wave. Sound travels faster through water and faster still through solids. It travels actually notoriously slow in air. You almost can't get sound to go any slower than it does through air. So number 6 on the notes is V equals F lambda, and that's there to remind you that, remember, there's only one way to change the speed of a wave. We've covered this before, but I want to make sure to drive it home. I asked you in class before, can I change the velocity of a wave simply by increasing the frequency? Many of you said yes. Mathematically, this is true, but scientifically, this is inaccurate. This does not happen. You cannot change the velocity of a wave simply by changing the frequency. The velocity is only controlled by the medium itself. And so right now I want to imagine that we're going to keep the medium constant. We're going to keep this sound in, let's just say, air. So the medium is the same, therefore the speed of sound is the same. Let's say 340 meters per second. However, it is true that we do have sounds that have different frequencies. And if they do, since this stays the same, it behaves very, very similar to another equation we had a long time ago. We referred to affectionately as the JFAT equation. Remember, this was impulse. This is the equation we used to explain an airbag. In an airbag, when you're in your car, whether you have an airbag or not, if you're in a collision, you're going to undergo the same change in momentum, which means you have the same impulse, because you're moving, say, 50 miles an hour, and you're going to come to a stop. Therefore, you have to undergo the same change in momentum. With an airbag, we wanted to decrease the force felt on your face, and since we can't change the J, what we could do was increase the amount of time for the impact. And so that's what an airbag does, is it increases the time, therefore the force can decrease because this one has to stay constant. Same exact effect with V equals F lambda. Since V is constant, then these two are going to be inversely related. If I have a high frequency sound, if I increase the frequency of a sound, since the speed does not change, since I didn't change the medium, if the speed doesn't change, the wavelength is going to decrease. That means the frequency and the wavelength are inversely related. As the frequency increases, the wavelength will decrease. This is, again, because the speed of the wave is only determined by the medium, and most of the time the medium doesn't change within one sound wave traveling. So if the medium doesn't change, the speed stays constant, and if the speed is constant, these two are going to switch places with each other. Frequency increases, wavelength decreases, and vice versa. Last 2 points. Frequency and pitch are related. When you hear a higher pitch, that means the sound wave has a higher frequency. Lower pitches have lower frequencies. And the loudness of a sound is determined by the amplitude of a sound. Remember, amplitude is how far, or the displacement rather, of each individual particle in the wave. So as a sound wave moves through, you have an air particle here that is vibrating back and forth like this. If I turn up the volume, that doesn't change the sound of the music I'm playing. The frequency stays the same, which means this particle goes back and forth the same number of times per second. But what it does is it increases the amplitude. This is the amplitude, the amount of displacement of the particle from its resting position. So if I turn it up, the particle does this. Turning it up greater makes it travel even more. It's covering a greater distance in the same amount of time because it has the same frequency. Therefore, the speed is increased, which means the energy of that particle is increased. So really, the amplitude of this wave is telling you about the energy of the wave. High amplitude, loud sound waves are transferring more energy to your eardrum, which may be here, which tells you why it may be dangerous to listen to loud music on a consistent basis, because you are bombarding your eardrum with very high amplitude, high energy air molecules. Those air molecules literally slapping into your eardrum, transferring lots of energy, and you could damage your hearing by doing that. All right, in class we talked about human hearing range, and when you get a free time, you might want to go to this website and do it on your own and just see if you can hear these frequencies. My guess is that you can hear all of these frequencies. Most of my students in class, most of you started to top out. You started to not be able to hear around 18 to 20,000 hertz. Some of you even heard 21 or 22,000 hertz. I would not be able to hear this 15,000 hertz sound. But just take some time, go and listen to that stuff. It's kind of interesting. This is where the mosquito ringtone gets its effect. The reason why I cannot hear as high as you can is because I'm older. And the truth is, when you were 6 years old, you used to be able to hear a lot more than you can now. And you've been losing your hearing. You've been losing the high portion of your frequency range ever since then. The human range of hearing is thought to be from about 20 hertz to 20,000 hertz. Again, that varies from person to person. Again, I had some of you that said you could hear greater than 20,000 hertz. But if you look at this graph, in terms of the rest of the animal kingdom, we're actually kind of not too impressive. The elephants can hear way lower than we can. Dogs, this is the dog whistle up here, they can hear much, much higher than we can. Things like mice, bats, they can't hear very low, but they have extremely high frequencies. Bats, that makes sense because they use sound to echolocate, as do dolphins and whales when they're in the dark. So we're not the only ones in the animal kingdom that use sound, and actually, in comparison to other animals, we're kind of pretty boring when it comes to our being able to sense sound. You need to understand these two terms, ultrasonic and infrasonic. Ultra is a term that simply means above, infra means below. So ultrasonic means sounds that are above a frequency of 20,000 hertz. Infrasonic is below sounds that are below or less than 20 hertz. This just means sounds that we can't hear. Again, this is centered on humans. Just because it's an ultrasonic sound doesn't mean that some other animal cannot hear it. If you start researching these other animals and see how they sense sound and what they do and how they use it, it gets actually pretty interesting.